father-in-law likes to say. All right, so real quick before we get started, we're going to finish up these midterm problems. Your official midterm grade is on My LaRoche, so if you're curious about any of it, let me know. I'd be happy to discuss your exam with you if you're curious about how it was graded and where you missed points. That's up to, but it's, you know, you just have to schedule a meeting, and we can do it on Zoom, all that fun stuff. All right, anyhow, I want to get back to this test problems, because as I said, there's this test, it's a take-home test. So there are what I would call fundamental and straightforward problems. Most of the test is that way. But being that it's a take-home test, there's also a portion of it that are more challenging, and also problems that are foreshadowing things we're going to do. They're trying to set the stage. Now, what happens is, the downside to that is, when I assign those types of problems, when you don't know how to do them, what you do is you go to the internet. And then, of course, you get the answer, and even sometimes it's correct and sometimes it's not, but then you just write down a number, and it's like, how the hell did you pull this number out of your head? And again, I don't give a crap, as they say, about the right or wrong answer. That is immaterial to me. What's more important to me is that you understand things, right? You know, you go into the internet and type in a problem in verbatim, and then copy and pasting what you see on Quora or one of these websites that gives you the answer, and you write down a formula that I know for a fact, if I offered you $1,000, you wouldn't know a damn thing that you wrote down. Like, that's not learning. That's just, it's weird to me, right? And not only that is it not learning, there's no evidence that you understand anything. So you got to keep in mind that fact, that it's more about how you describe your thought process in your work. You're more likely to get points if you do something wrong, but you at least have a good motive for what you're doing. If you just write a number down without any, you know, like some of these numbers, you don't just pull them out of your head. It's not like 3 + 5 is 8. Like, some of these things are very complicated, and the only way to see them is to have a sort of way of viewing it, and just writing a number down is not the way. So a good example of that is problem 4. Let's talk about number 4. First and foremost, let's talk about 4. Although I do appreciate some of you actually telling me where you get your numbers from. I got it from this website, or I got it from that. That's fine. It's better than nothing. But. All right. So we sort of did problem A in class as an example. I forget if it was a homework or not. It might have been, but I know we did it. And we broke it down. And the point of this is to foreshadow that there's got to be a clever way of doing certain counting. That's the point of this. So here's the thing. We roll 6 standard die. And so what's the probability you roll at least 1 3? Well, that's equal to the probability of everything happening minus the probability that you get no 3s. So this is a problem where using this complement is the best way to do it. Now, the way to think about this is, how many ways are there to get no 3s? So this is what we're trying to think about. How many ways can you get no 3s? Well, one way to get no 3s is the only way to get no 3s. The first dice has to be a 1, 2, 4, 5, or 6. The next dice has to be a 1, 2, 4, 5, or 6. There is only one possible way to get no 3s, and that is every roll pops up non-3. Now, what we can think about is whether I roll all 6 dice at the same time, or if I roll 1, pick it up, roll it again, pick it up, roll it again. It doesn't matter if I have 6 dice or I roll the same dice 6 times, 1 die. It's mathematically equivalent. And the fact of the matter is, what happens on the first roll has no bearing on what happens on the second rule or the third or the fourth or the fifth or the sixth. And so because of that, we have these probability rules. All right. And these probability rules tell us that there's a pretty straightforward way that we can compute this thing. So what's important you understand is there's only one way to get no threes. And so what is that? What do I mean by that? Well, that is roll one or dice one, no three. Roll two, no three. All the way down to roll six, or if you want dice six, it doesn't matter what you call it. And so the probability here of no three is 5/6. Why is it 5/6? Because there's 5 out of 6 options work for this guy. And then the probability that no 3 happens here is 5/6. And then, of course, all 6 of these guys, if you will, this are 6 dice or 6 separate rolls. It doesn't matter. So let me explain this again. If I can either take 6 dice and roll them all at once, or I can take 1 die and just roll it 6 times. That is mathematically the same thing. And so the fact of the matter is the probability that I don't get a 3 is 5/6, because any other roll is a success, where rolling a 3 is the failure. Now, what does this mean? Well, because since each roll or die is independent of the other, the probability of no 3 is equal to the probability of no 3 on first times the probability of no 3 on second, etc. And we do this all the way down to the probability of no 3 on the sixth. And of course, this is 5/6 times 5/6 times 5/6. And how many times do we do 5/6? That's 5/6 to the 6th power, because there's 6 of them. Now, I could have just multiplied all this out, but the key here is if we multiply everything out, we lose out on a pattern. And that's what we're looking for. We're looking for a pattern. Does anybody have a question about this? Okay, so what is the conclusion then? The conclusion is as follows. The probability of at least 1 3 is equal to 1 minus 5/6 to the 6th power. And then, of course, you can go to a calculator. And you can compute this. Oh boy, that ain't correct. And what you end up getting is you get approximately 66%. Well, really, you get 0.66. How about, let's just approximate it, 6651 or 66.5%. So what happened on the test is many of you just wrote problem 4A down and then you just wrote what's in green here. What does that mean? That you're a good Googler? Yay, you can Google, right? Even if you could Google, that's fine. I ain't mad about it. But then you got to write down why this is true, though. That's the learning experience. The learning happens when you understand why this is the case. And then what's even more illustrative here is if you understand why this is the case for this particular problem, you can generalize these ideas to all kinds of problems. And that's what's very useful. That's the big key in all this. That's the pie in the sky. Another important theme here is you can think about rolling a 3 as either a success or a failure. Either get a 3 or you don't. Sort of like you either flip a heads or you flip a tails. You either live or you die. The medication works, it doesn't work. The loan is paid, it's defaulted. The student passes, the student fails. You got it correct, you got it incorrect. It's another way to think about these things. All right, so this is the problem. We actually did this in class, but I caution, when you're writing solutions down, nobody, particularly in the math or science world, wants you to write the number 4 and then part A and then just write 1 minus 5, 6 to the 6th. That means nothing. You should be striving to write solutions so that somebody can read them and learn from them and understand from them. If I just wanted a number, I would just give you 50 multiple choice questions. Anyhow, I hope you take that in consideration. All right, now the next part is quite challenging if you try to solve it in a natural way. So for part B, we now have 12 dice, or if you want, or 12 separate rolls of 1 die. It doesn't matter how you think about it. They're mathematically equivalent. So some of us understand it in different ways. And so the question then asks, what's the probability that you roll at least 2 3s? So the probability you roll 2 3s at least, I got to be very careful because that's a different. Is 1 minus the complement. Well, what is the opposite of rolling at least 2 3s? That means you either get 0 or 1. So let me write that down because I don't think we understand that you need the complement of this. And this is 1 minus the probability none or exactly 1. And using our rolls, our probability, you can't roll it 12 times and get none and 1. It doesn't make sense. They are exclusive. And so our rolls of probability by the axioms tell us that this means we subtract the probability of none plus the probability of exactly 1. Now, this part that I've gone to right now, this is the theoretical things behind here. These are the axioms. These are these theorems, these rules of probability. This is the learning. This is the cool, like, reasoning part of the problem. You know, the moment you don't do any of this and you just go and type it right into the internet, which guaranteed if you verbatim this into the Google search, it's going to tell you the answer. Probably won't tell you why. And in fact, that's probably how most of you who got the correct answer got it. No offense to you guys. And that's okay, but what's more important, in my opinion, is that you read and understand why, you know, part of me putting questions on here that even the best students are going to struggle to get without help from the internet is to show you how to get help from the internet. The #1 resource. Everything that human beings know is right here, right? And almost every one of you has access to this, even if it's not on your phone. You go across to the library and it's there. You got to learn how to use it. You know, the first thing I do when I don't know something, Google it. And I know you had teachers your whole life to say, don't trust Google and Wikipedia, it's bull crap. They're idiots. And if they, you know, if they tell you otherwise, I'm telling them. Are there citations on Wikipedia? Yes. It ain't phony. I always hated that. Don't use Google. They always want you to use some weird search engine on a library webpage. Google it. Google it. My favorite thing about finishing my dissertation, I said, what should I use for my works cited? You know what they said? You're the author, whatever you want. Think I got -10 on my dissertation because I didn't use whatever the hell, I don't even know what the hell they used. Works cited this. Just give credit where credit is due. That's all anybody cares about. Okay, so anyhow, this is how we set the problem up. And really, this is not, the hard part of the problem is still to come. At least knowing what we've learned in this class. And that's another thing that it's sort of, I don't want to say annoying, but oftentimes when you guys go to the internet, it's a sheer sign that you didn't learn what you're doing when you write things down. And there's no way you know what the symbols are. You just write them down. And if you did know what the symbols were, you would tell me what they were. You would just write the damn things down. Like, you know, like number problem 6 on the test, I set that problem exactly, and I knew it was going to happen. About 2/3 of you are going to tell me blah, choose blah. You don't know what the hell it meant, but you were ready to write it down. All right. Anyhow, back to this problem. So we already know what the probability of none is. For the same reasoning above that we had above, this is 1 minus. Now, we can't do 5/6 to the 6th because we don't have 6 rolls anymore. What we have is we have 12 rolls. So we have 5/6 times 5/6 times 5/6 times 5/6, 12 times, because there's 12 ways I can either get a 3 or not get a 3. Now, this part right here is the challenging part. How can we reason what this is? Well, we showed you how to reason this probably 2 weeks ago now when we did part A in class. And all you had to do was generalize that reasoning instead of doing 6 dice to 12 dice. So here we go. So how can we get exactly 1, 3? Well, let's look at the scenario. So let's say let 3 equal rule of 3, and let n equal not rule of 3. So let's look at the scenarios. So if we get exactly 1, we can have a 3 in the first position. No, 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 no. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that correct? Let's count them. 1, 2, 3. That's one option. That's one way I can get exactly 1, 3. And then the next scenario is no 3, 3. No, 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 no. You following me with this? Maybe? I don't know. And then, of course, the next option is no, no. And then we get a 3 on the third die or the third roll. No, 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 no. Now, you could write all these out, and there's going to be how many of them? This goes on 12 times. All the way down to the very last scenario where you get a bunch of no's. And then the very last time you roll a 3. So if you want, you can call these 12 different scenarios. Now, the beauty of this, if we understand patterns, that every one of those scenarios has the same friggin' probability. Because what's the probability I get a 3? 1/6. What's the probability I don't get a 3? 5/6. Now, getting a 3 on the first roll or the first dice does not affect what happens on the second through the 12th. They're all independent. Yes?
Why is it 1/6 and not 1/12?
Oh, yeah, because from each, that's a good question. But remember, what is each dice? Each dice has how many options? 6, right? So that's a good question. That's a very good. So the question was, why is it 1/6 and not 1/12? Remember, 12 is the number of times we're rolling it, or you could think about 12 being the number of dice we roll. However, each dice has 6 options, 1 through 6. Does that make sense? You sure? That's a good question. I've messed that up before too. You gonna dance? I'm gonna move to dance. It's Weekend Wednesday. I hear rumors that everybody, the Ronies, getting everybody. Yeah, man, you guys stay sleep on the Roni. That's what we say. Don't sleep on it. I shouldn't joke about these things, right? Amy just texted me, my youngest crumb snatcher. I knew something was up. She kept burping and making all kinds of belly noises last night. Now she's vomiting everywhere. Can you believe these crumb snatchers? They don't care about washing their hands or germs. They just get sick. Mm-hmm. That's what crumb snatchers do. They snatch crumbs and get sick. What a time to be alive. She's got this new thing where she likes to sleep on the couch. So like 4 in the morning last night, so I got, Daddy. And then of course she does this. It's like, I think my wife trains her to say Daddy so that my wife don't have to get up. Then I feel guilty and I got to go lay on the couch with her. And she lays there and just was like all night long. I was like, oh God, kids these days. All right. Okay. Are we cool now with this? Are these scenarios? Are we okay? All right. Now, every one of those guys, each one of those 12 guys, there's 12 ways. So here's the scenario. So all 12 scenarios have probability equal to 1/6 times 5/6 to the 11th power. Because there's 11 no's and 1 yes. I'll tell you what, you guys probably hate this. I love this crap. When I figured this out years ago for the first time, it was like the greatest thing. Because then I figured we can gamble and I can take everybody for their money, right? Like imagine this game. Think of this game. I just taught you a badass game. You can now, if you do this problem correctly, that here's what's going to happen. Think about this. If you do this problem correctly, you could trick your friends. You could say, we're going to roll 6 dice. And if I get at least 1 3, I win. And then you're going to roll 12 dice. And if you get at least 2 3s, you win. And guess what? Your friend who ain't paying no mind to O'Grady and probability will probably pick scenario 2 because there's more dice. They'll think, more dice. I got a better chance to win. Then you steal all their money. Because even though there's more chances to win with 12 dice, there's also way more chances of losing. Right? You get 5 no's with 6 dice. You get 11 no's with 12 dice. Anyhow. Okay, so each one of those has probability of this. And so what we do then is our axioms and rules say that the probability of exactly 1, 3 is, let's not write is. So each one of them can't happen. They're mutually exclusive, if you will, right? I can't have scenario 1 and 5. And I can only get one at a time. So that means, what do? I add them up. I add them up. So this is equal to the probability of scenario 1 plus the probability of scenario 2 all the way up to probability of scenario 12. And of course, they're all the same, so we're really adding up 1/6 times 5/6 to the 11th. We're adding this thing up how many times? We're adding it up 12 times. And you learned as a child that a nice little shortcut for repeated addition is called multiplication. And even though this looks scary, this is 12 times 1/6 times 5/6 to the 11th power. What a time to be alive. Oh, man. I can't believe we're setting so much awesomeness that you guys will be able to discover the binomial distribution on your own. It's like, what's that old thing they say? If you teach, or if you give a man a fish, he'll eat for a day. If you teach a man a fish, or a woman, she will eat for a lifetime. I cover all bases here.
Nice cat.
Hmm?
Nice cat.
I'm here for you. It is wild. You think about it. You read any science books before like the last 30 years, almost every science book, the author would have never thought in a million years that a woman would read it. They'd always say the reader, he or him. There's never that a girl might want, or a woman, I should say. I got yelled at last semester, 2 semesters. It's not the girls' basketball team. It's the women's basketball team. I said, you ain't even lying. All right. This is conceptually challenging, but I hope we've sort of massaged it in a way that maybe it makes a little sense. I hope. Does anybody have a question to this point? So we did all this work, and now we finally come to the exciting thing. We could put this all together. Conclusion. The probability of at least 2 3s is 1 minus the probability of none minus the probability of exactly 1. And this becomes 1 minus, we know this one is 5/6 to the 12th power. And this is 12 times 1/6 times 5/6 to the 11th power. And I'm not going to lie to you, a cool thing to take from all this is not just why is he writing all these ugly fractions and powers, but there is a clear freaking pattern here. Now, it ain't going to be as clear to you because you're amateurs, but there is a pattern here. And maybe it's not as easy to see because I write sloppy as you know what. But there's a pattern here. And what happens is if you go and you plug this stuff into a calculator, I am going to do that right now as we speak. I hit the wrong button. What is happening? Our pets' heads are falling off. So if we do this correctly, we get 0.6, what is it, 0.618 approximately? So let's put approximately 0.618, or if you'd like, 61.8%. So you're less likely to roll at least 2 3s with 12 dice than you are to roll at least 1 3 with 6 dice. This is actually a famous problem. It dates back to some legends, Newton, some other smart nerds back in the heydays for gambling purposes. We could start our own casino, the Math 1040 Casino. That's what we should do. If we want Neroni, we can have a thing. We'd have a casino down in the center, the square. We'd get rich off it. That's what casinos do. They rob the fools of all their money. Anybody here like to gamble? Blackjack, baccarat, craps, poker. You have a poker tournament. That's what we can do too. When I was in grad school, I thought I shouldn't say this on the camera, but I knew these guys. They're wealthy and they were smart with gambling, and they would go to Vegas all the time. Leave Friday, fly back Sunday night. Gambling's fun. No, yes it is, if you're smart about it. Okay, again, this is a challenging problem. And if you want to learn anything from this, what I would highly suggest is that you don't just say, oh boy, but think about this, particularly how I reason this number over here. This is where the magic's happening. And how did I reason this? Because there's really a general theme here that we're going to start talking about probably on Monday. And there's this thing called the binomial theorem, which most of you used, even though you didn't know you were using it, because you just copied the answer off the internet, which is okay. I'm not mad at you. In the words of the late, great Heavy D, which none of you probably know, he would say, I got nothing but love for your baby, which I have to amend and say, I got platonic love, because that would be creepy if it was otherwise. All right. So this is a challenging problem. Hopefully, maybe you'll spend some time thinking about it. All right. Now, if problem 4 wasn't challenging enough, I love this. See, 5's another brilliant one. Boy, you guys were using things. There ain't no way in hell you knew what you were using. You're writing down expectation. I'm like, what? They don't know what it is. Geometric distributions. Oh, you guys out here, so cute. I was like, oh, geometric distribution. That is so great. Of course, your argument, you gave us a problem that we can't solve. No, that's not true. You can solve it. You have to reason it. But there's always going to be a shortcut. That's the beauty of advanced mathematics. It turns complicated things into simple things. Macintosh, I'm telling you, this is what you need to think about. What time is it? It is so funny how trained we are. I'm literally looking at my phone to see what time it is, because that's what habit is. And I have clock here. I have clock here. Clock there. What a time to be alive. Now I have to close this down. Then I saw these people. What is that? I saw someone complaining on the internet. You're like, you ever hear like the old people complain about like smartphones ruin people because, like, you know, back in the day, people talked when they were like the airport or on a bus or something, or a subway. Now everybody just looks at their phone, which is so full. You ever see like a picture of a subway in 1960? You know what everybody did? They sat with a newspaper in front of them, or a magazine, right? Or you go to a doctor's office, there was magazines everywhere. Now everybody looks at their phone. Someone said the other day that there's 2 bedtimes now, the time you lay in bed and then the time you put your phone down. And I said, people been reading in bed since the dawn of time. Well, since the dawn of books. In candlelight, I guess. Right? I love people. Old people love to complain about us. See how I try to tie myself in at your ages, like we're all the same? All right, so really, here's a cool thing. Problem 5 is a challenging one. This is the famous Biden versus Trumpster problem. Or as Trump calls him, Sleepy Joe. I don't have a good nickname for Trump. All right, he was moonwalking the other day, I saw. What a legend. Good God, can you believe this is what the world has come to? These 2 buffoons are going to be in charge of the free world soon. One of the 2. Anyhow, really the only question that's simple to answer is problem 1. or part one of this problem. So number 5, the only one that is simple to answer. So here, here's really what we're saying. We're going to toss a coin until we get heads. So the probability it ends on first toss, well, that's really the only thing we can maybe answer. Notice I'm saying maybe. So the only way it ends on the first toss is if you get a heads first. So let's just assume that we think that's a half. It seems reasonable. Well, then you might get misled because you might say, what's the probability it ends on the second toss? So a lot of people wrote that it's 1/2 times 1/2. But do we know that? See, this is a different sort of, the way we're thinking about this experiment is different. Right? What is the sample space of this experiment? Technically, we can write it out, but if we want to think that it ends on the second toss, that's only if our sample space meets a certain criteria. So let's think of the sample space. Our experiment says we're going to flip a coin consistently, and then the experiment ends when we get a head, right? So the first thing is it could get a head on the first try. Game's over. If I don't get a head, I can get a tail, then a head. Then it ends. Another option is I get 2 tails, then a head, or 3 tails, then a head. The fact of the matter is this pattern, there is no end. So this is the first example that I've given you guys so far of an experiment where the sample space is in many ways what we'd say not finite. So since the sample space is not finite, that makes us maybe even question this. Now our intuition tells us we flip the coin once, there's half chance it's heads, half chance tails. So maybe we're confident that the probability that it ends on the first toss is a half. But should we be confident that the probability that ends on the second toss is a fourth because the probability of tails and heads is 1/4? Should we? I'm not saying the answer is yes or no. I'm saying this to make you think. Don't confuse the probability of getting tails, heads in this scenario is the same thing as flipping a coin, say 5 times and getting tails, then heads. Now, again, I'm not saying it's wrong. I'm writing question marks here for a reason. So what I was really looking for in this problem was I was looking for you guys to reason more with words than with numbers and formulas. Now, it's not wrong to reason with numbers and formulas. In fact, there is a correct way to reason this problem. And we're going to have to invent new things. This thing that some of you use called expectation. There's this thing called, the fancy word for what you could use here is what's called the geometric distribution. And I don't know if any of you have had any familiarity with things. Maybe some of you have had calculus before, I don't know, and you understand what we call a geometric sequence or a geometric series is, I don't know. And these are things that we might touch on soon enough. But and even if you didn't really think of that, even if you went to the internet and went and got answers about this, what I was hoping is that you would somehow reason what these symbols and things that you wrote down meant. So in many ways, I don't think of this as just as like a test. Let's test you on problems. I also think of this as, I don't want to call it a research project, but if there's something you don't know and you go to the World Wide Web or to a textbook or to someone and try to learn, I expect you to report back what it is. Don't just copy something verbatim without explaining it, right? At least show me that you've learned something. That's another aspect of this that, you know, I kind of would hope that you do. But anyhow, as some of you found out, that there's a sort of a formula to answer this, and it comes from this thing, whether you knew it or not, which is called the geometric distribution. So these are the kind of ideas that I would like to foreshadow. And then say, for example, and I know I'm being bland with my answers here, and that's on purpose. So like, for example, which player is more likely to win? Well, wouldn't you just immediately, if the first person's gonna, if you think that the chance it ends on the first toss is 1/2, then there would be no other rationale than it has to be player one. Because in many ways, it's almost like they get an extra toss, right? Does that make sense? So let's write it this way. Intuition suggests player one. The questions you might immediately ask is, but by how much? And more importantly, what I like to know is why. And then if you reason that player one is more likely to win, then you would say no. I mean, if you're the Donald, you would want Sleepy Joe to go second, right? Or if you're Sleepy Joe, you'd want the Dawn, or whatever the hell he calls himself. I love it. What a time to be alive. The fact of the matter is, you would imagine that you would want to go first if you had a choice. And that is because you know that it's at least, you think at least a half that you're going to win. Let me rephrase that. At least your intuition suggests the player who goes first has more than a 50% chance of winning. Why would your intuition maybe suggest that? Well, again, whoever goes first at least has a 50-50 chance. Of course, then you might argue, well, if they don't win, then whoever goes second has a 50-50 chance. This is an interesting problem. Before we do anything else about this, does anybody have a question about this particular problem? And I was very lenient with how I graded this, by the way. I wasn't like crushing you. I was looking for interesting takes on it. I was looking for interesting thoughts. I wasn't necessarily looking for correct math. That wasn't the point of this. Now, correct math is nice if you explain it properly. And there's lots of cool ways you can reason this stuff, by the way. You can use, so here's another way to think about this problem, which I would encourage. Say the coin's flipped and it's tails. So at the second stage of this game, everything is the same as it was at the first stage, right? Does that make sense? Like, the coin don't know that the game's not over yet. It doesn't say, oh, damn, I threw a tails. Let me throw a heads. It doesn't know that. Okay, so say our intuition is here. Now, sort of the way I designed this problem is I say, okay, so how long do we expect it to last, and then why? Well, here's the one thing. We know it can, the minimum it can last is 1 toss, but it can also last 1,000,000, right? It can last 10,000,000. Now, that's very unlikely. It's highly unlikely I get 1,000,000 tails in a row, but technically it could happen. How would I reason how long I think the game should last? Well, okay, so another way to think about this, and again, my job, I feel, is the instructor here is to sort of give you problems that help you learn. And I also think it's some more to, I don't want to say inspire. That seems like a weird thing. Some of you really don't care, and I don't blame you if you don't care. But to give you some sort of teachable moments to sort of, as I said earlier, lead you, not just lead you to the water, but sort of teach you how to think about these things, teach you how to fish. How do you think about these things? When is intuition useful? When is intuition, I don't want to say bad, but when can it mislead you? Intuition can mislead us lots of times. So, for example, maybe we'll think about it like this. So here's one way to think about it. Create, instead of thinking about just heads and tails, let's think about the sample space and let's think about the idea of this. Let's, instead of saying what's, what is the event, we get a heads or a tails heads or a tails heads, let's think of it like this. What is the event that we end here? Or what is the event that we end here? Or let me, instead of event, how about outcome? If we think of all these outcomes as just members in our sample space, we can ask, another question might be, what is the probability the game ends on the first? What is the probability the game ends second? What is the probability the game ends third? What is the probability the game ends on the fourth one? So what you can do is sometimes use that idea, combine that with the idea that what happens at the second stage, it doesn't know what happened in the first stage. And what happens in the 14th stage, if we get that far, it doesn't know what happened in the first 13. That coin ain't thinking about how many times it's come up heads or tails so far. At least we don't think it is. So what we can understand is that these sort of, each step of the game, one way to think about it is what's called many-less. So what if we said, okay, can we ask, what's the probability the game ends on some kth flip? Would this be easier to analyze? So we know what the sample space looks like, but it doesn't make sense, at least since this thing is finite. We can't use this notion of probability where we take the number of outcomes divided by the total number, because we don't know the total number. It is plausible, although not likely, that the game never ends. Well, I shouldn't say never ends. It will. Turns out it will end eventually. We know that first. But the fact is we don't know how long it's going to take. So here's an event. So let's say A. Let A be the number of tosses until a head appears. So if we look at our sample space, so we had heads, tails, heads, tails, tails, heads, tails, 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 heads, etc. So if we think about this, here we get A is equal to 1. Here is A is equal to 2. Here is A is equal to 3, etc. So note, what can we say about, sort of the relationship between these A's. Well, we know that the previous one is 1 less than the guy that follows it, right? I mean, this guy would be the 4th. So what I'm hinting for here is there some way I can invoke or introduce these ideas from, or these axioms, so to speak, or not necessarily my axioms, but my rules that we've sort of discussed from these axioms. Can we sort of relate consecutive values of A using some sort of algebraic formula that we can make a deduction? So let's think from our intuition standpoint. Do we expect that the game's going to end at like A equal 30? Like intuitively, do we think the game will last that long? Probably not, right? We would probably guess that a game will end in like the first couple steps. But the key thing that I mentioned about 5 minutes ago is that if I'm at the 3rd step right now, and suppose it doesn't end at the 3rd step, suppose I get 3 tails in a row. The game ending on the next step has to be the same probability that it would have ended from 2 to 3 or from 3 to 4. Right? So here's what we know. So the probability game ends on 8th toss is equal to the probability it ends on the 8th or the A plus 1th toss. Right? Maybe I shouldn't phrase it this way. Maybe I should ask you this. Put a question mark there. So maybe I'll leave you at this. And again, we're going to come back to this, but in order, at least in my opinion, if you want to gain some cool stuff out of this, it's great to think about this before we tell you the answer. So if even one of you thinks about it, that's great. But what I'd like to do is, and before we leave, I just want to cover the last problem. So we'll leave you with this real quick. Can we determine some equation for A? And so that's where we'll leave you. Now, again, we'll come back to this, I promise, but I would hope you give it some thought. The last thing that I want to do real quick is, because we're out of time, is I wanted to talk about the last problem on the test. And so the last problem says this. We have a bag. It has 26 plastic towels. Each one of them is the same. It has a different letter of the English alphabet. I want to pick 4 towels. What's the probability it spells math? So in order to spell math, I didn't say that you had to spell it in order. I just said you had to be able to spell math. So let's think about this. The pick one, how many options, if I want to get math out of this, what is the probability I pick one of the correct letters? Well, how many letters are in math? There's 4. So I have 4 options at first, and there's 26. Then my second pick, if I've already picked one of the correct letters, there's 3 correct letters left. So that would be 3 over 25. And then my third pick, there are 2 correct letters, and that is over 24 because there's 24 letters left. And then finally, pick 4 would be, there's only 1 option left that's going to work, and then there's only 23 total guys left. Now, the way I would tell you to think about this is to not multiply it all out yet, although you could, but the key to the pattern here is that the numerator is 4 times 3 times 2 times 1. And the denominator is 26 times 25 times 24 times 23. And these types of products arise a lot. And we adopt, for those of you who don't know what this is, and we're going to get into it soon enough, if we use factorials, and if you don't know what that is, that's okay, you'll know next class. Using factorials, we can write this in a slightly different manner. This is what we say 4, and it's an exclamation point, but this reads factorial. And then downstairs, this is also a factorial, you just don't realize it yet. What it is it's 26 factorial divided by 22 factorial. Another way of writing this, using what you've learned in arithmetic class about a fraction where the denominator is also a fraction. When you were a kid in school, you learned a fraction over a fraction is the same as multiplying by the reciprocal type things. So this turns out, and this is what some of you used, and I don't know how you knew it or what you're doing, but there's these things called permutations and combinations and binomial coefficients that we will start to use soon enough. But this can be rewritten in what we call the following way. We use choose. So some of you use this. I don't think you had any idea what you were doing, and that's okay. This is 1 over this. So what is this creature? What is this 26C4 thing? These are called binomial coefficients, or they're called a K combination. And hopefully, I shouldn't say hopefully. What did I just lose what I was doing? I keep losing the homework. Did I write it down right? Yeah. But anyhow, what this turns out to be, whether you recognize it like that or not, is this turns out to be approximately 0.0000668. So it's very unlikely. So we will tell you, the stuff that I've written in blue, we're going to talk about that next. But what this 26C4 means is if you have 26 things, what this is asking is how many different ways can I select 4 things from 26 things? That's what it's asking. Now you might say, well, what does that have to do with the problem? Shouldn't it be upside down? That's another good question. Does anybody have any questions about this? Going once, going twice. All right. By the way, let me just say something real quick. Why is this shortcut that some of you used? Why is this correct? Well, how many ways can you spell math? You can spell math one way, right? And so what this denominator was, is this is how many different ways can I take 26 letters and break them into 4? How many ways can I take 4 letters out of 26? And it turns out that it's like 14,950 different ways you can do it. And since you can only spell math one way, it's 1 divided by that for the probability. That's one way to see it, and we'll examine this problem from that angle. But the other angle, the easiest, or the intuitive angle, is the way that we did it here. Anyhow, thank you guys. I appreciate it. Please ask me any questions you have via email or whatever, and have a good one. I will see you Monday. And if you've emailed me and I've yet to respond, I will get to you soon, I promise. All right, guys. Thank you.